Ladies and gentlemen, welcome to our webinar this evening, and thank you for attending, especially to those of you who are members of one of our institutions. My name is Dion Rowley, and I will be acting in my capacity as committee member and chair of the Joint Institutions Lecture Series by representing the IET, Engineers Australia and the IEEE this evening. For those of you who may not be a member of one of our institutions and would like some more information on how to join and the benefits, please check the links at the end of the presentation or contact me directly. The Joint Institutions Lecture Series is a collaborative arrangement between the Institute of Engineering and Technology, Engineers Australia and the IEEE, where we work together to bring you a diverse programme of technical events and meetings to provide continuing professional development and networking opportunities. During the current restrictions, we aim to continue bringing you these events via our web-based platforms and look forward to physical events in our new location in the centre of Sydney, Australia. Just before we start, I would like to give an acknowledgement of country. Engineers Australia and the Gills Committee acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures, to elders both past, present and emerging. For the purposes of this live presentation, all participants will be asked to mute their microphones, and we encourage you all to submit any questions that you may have using the chat box provided at the bottom of the screen. For those of you who may be watching this event at a later date, there will be a Q&A session at the end of the presentation which will address a series of questions which were raised. Tonight we are privileged to have two presenters, Ida Garikani and Sten Iverson, with us, who will be talking about their work to support the design of PCBs for high-speed data applications using CAD tools. Sten Iverson started his career in the Royal Danish Navy in mechatronics, later as an electronic design engineer for Ericsson, Denmark. In 2011, he founded Microdesign, a freelance consultancy company. After that, he taught students electronics at Aarhus Tech before joining Altium as a field applications engineer. Sten will be joining us this evening via video link from Denmark. Our first presenter, Ida Garikani, studied her Bachelor of Electrical and Electronic Engineering and completed a Masters of Engineering in the field of Mechatronics, Robotics and Automation Engineering from the University of Western Sydney. Other accolades include certificates in microcontroller programming, project management principles and practice specialization from UC Irvine, California. During the past few years, Ida has gained industry experience as an electronics design engineer and project/operations manager at Altium. Well, that's enough of me talking. I'm sure you're here to listen to the wonderful presentation. So without further ado, would you please virtually welcome Ida Garikani to the podium.
Hi everybody, this is Ida, field application engineer from Altium. And today here is with me Sten, field application engineer from Denmark. I'm going to do the presentation today, and at the end of my presentation, he's going to have a demonstration on software Altium Designer.
Hello, Ida, and thank you for the opportunity to be here.
Thanks, Sten. Okay, guys, welcome to High-Speed PCB Design seminar. And I'm going to today speak about what is high-speed design, and then also crosstalk and EMI. The topic we have for impedance and transmission line, return path, and also routing and differential pairs, impacts of vias, back drills vias, and at the end I'm going to speak about X signal multi-chip and signal integrity. So for the first topic, high-speed design, actually, what is high-speed design? High-speed design is the art of managing the flow of energy from one point on a circuit board to another point. So as you can see here in this formula, we have this propagation velocity, which is very depending on the speed of light and also dielectric constant. So next, a signal travels at the speed of the light, as we know. And in the picture, as you can see here, we have a signal, a rise and fall time. And actually, this time is from 10% to 90% of the signal level. And in another word, we can say this time it takes from logic 0 to 1 or 1 to 0. So what is flight time and signal skew? So flight time is the time it takes for a signal to travel from output to input. And signal skew, any difference between the arrival times of the beats. So the fact is very important here for high-speed designs. It is the length, materials, component placement, and also matched length. So now let's spend time and understand what is crosstalk and how it actually appears. In signal integrity language, the signal that is radiating the energy is referred to as the aggressor net, and the signal that is receiving the crosstalk energy is referred to the victim net. And as you can see on the picture in the presentation, we have the victim net and also aggressor net. The other things in Altium Designer, we have the signal integrity, which is before you try to push everything from the schematic to PCB. So you can try this in signal integrity and find out the issues with the crosstalk, which you can see in the picture. And now the next thing is about electromagnetic interference, which is EMI. What is that? What is EMI? The electromagnetic energy that is traveling around the route as part of each signal does not all couple into target input pin. So some of it escapes and interferes with adjacent signals. So this escaped energy becomes what is we're calling it EMI, and when it couples into a neighboring signal, it creates what is actually we're calling it crosstalk. So in the engineering design and the PCB is very important, the EMC standards, which is we have to make sure this designing for EMI immunity, which the two factors very important is a right stack up, and the other one is routing strategy. And also conducted and radiated EMI is important here as well. And again, we have the items very important here is the layer stack, grounding strategies, and component placement, which is very important here. So now let's a little bit spend time on here and understanding what is impedance. So stack up impedance, as you can see here, we have two layers, layer 1 and layer 2. And between these two layers, there is a capacitance, and the materials is very important here. So the things is very important for the impedance is the areas, distance, and dielectric. And the transmission line impedance, which here we wanted to understanding what is it, this transmission line impedance. So first of the thing is impedance is the value determined by the voltage to current ratio of the traveling wave. And as you can see here, so impedance is very important as the important ratio. The two factors, important things is inductance and it is the capacitance. So if I go to the next here, now you might understand more what's impedance matching. So we have the source and we have a load. And from source to load, we have a transmission line here. So it's very important to matching source, transmission line, and load impedance. All these are matched. And as you can see on the picture left side, we have a good impedance match. And in the right side, we have a very poor impedance match. We have a lot of overshoots at the beginning of this stage. You can see the overshoot and undershoot. So we don't want to see this overshoot and undershoot in impedance. So the parameters is very important in impedance are like conductor width, they are the thickness of dielectric and dielectric constant and thickness of copper. So as you can see here, we have the kind of strip lines, the different transmission lines here as an example in the picture. And then both of them, they actually very important. The facts is it is width and also the thickness of dielectric H and W. Now let's understand a little bit more of the layer stack up and understanding the dk and df in impedance. So as you can see here, we have a layer stack up in Altium Designer, and also we have a df, dk in the layer stack up, and also some other things like materials, and we have a demo at the end of that for you guys. You can see how that works. But at the moment, what is dk? Dk is the dielectric constant, and it can store more energy than materials with lower value. But at higher dk values, electromagnetic energy will flow at a slower rate through the conductors. And df, actually you can say it as dissipation factor, which is a tangent and loss tangent. These two is very important facts, and df, it is very depending on ESR, as you can see in the formula down in the presentation. So now the other things in the layer stack up I wanted to show you here is a materials library. Is very important in high-speed design, and we have materials library here, as you can see that in the core and the other materials, but you can also create your own materials if you have any data sheet anywhere else. So you can go to new and create the materials of the library materials. But this is the fact is very important for the high speed design. So next is here, it's the impedance profile, which we're talking about it, how to create the profile, impedance profile in a layer stack. We will have a demo for that. And also the next is here in the presentation, you can see when we create the impedance and then you apply it in each layer. So in the right side and left side, both you can see the items which is we are talking about the transmission line structure, and also you can see down there this is the transmission line parameters, which you can calculate it automatically in Altium Designer. So this even apply for differential pairs. So we have the similar thing in the differential pairs, and you can apply this impedance for them as well. So if you're looking at this a little bit closer, you can see the trace impedance, the calculation, and also transmission line. And this is actually very dependent on this calculation to take it to the design rule and using it in your design rule, which we are going to have a demonstration on that, how to use the impedance profile in your design rule. And here as well, you can see it. This is the design rule here, and apply the impedance profile 50 ohm, for example, and you're also able to see the all layers with the thicknesses and the different value. You can see it under that impedance profile in the design rule. So the other one we have here for differential pair. So it's going to apply for both differential pairs and single layer. So I'm going to next slide here and take you to the important applications. It just reminds you and remember that to couple signal layers to planes, and also to have the thin core for consistent impedance, and in the third as well, keep same layer whenever possible. This is the highest speed design applications for you. And let's understand where does actually the return energy flow, and we're talking about the return path. Electrical energy actually only flows when there is a closed loop. Actually, you can see it here in the picture as well when I'm just talking about it in here. So the energy flowing out along the signal route must also have a return path. So the returning energy of a signal wants to flow back along the same twisting and turning path that the signal route took across the board. So also have in your mind that this is causing EMI if we don't be careful about this, and this is in a high speed signal. This is the crosses the split in a plane, a loop is created, and that's actually causing the signal to create EMI. So here, how to managing this return path, we can creating the parallel planes. For example, creating parallel plane with a plane layer, or creating a parallel plane with polygon on a single layer, which is, you can see it in the right side. We have the two pictures, which is one is for plane layer and the other one is a polygon. So the other method, the other things I want to just talk about on here is creating return path design rule. So as you can see on the picture here, we have the design rule in for return path, and also we have the impedance you can apply for these design rules in Altium Designer. So let's little bit speak about monitoring the route length. So as everybody must know, and you guys know, estimated length, it is equal current routed length plus distance from current location to target path. And as you can see in the picture here, so in Altium Designer, you can actually specify this is the single, the signal is that based on the length or is based on the delay. So let's talk about a little bit differential pair here. And coping with crosstalk, because the radiated energy couples into both the outgoing signal and the return signal, creating what is called common mode noise. If there was only a single signal, this crosstalk would add to that signal and distort it. But the differential pair input pins are designed to look at the difference between the pins in the pair, and so can reject the common mode noise. So to make sure two signals arrive at the same time, so we are using the design rule matched length, and you can find it in the design rule in Altium Designer, and you can apply it for the differential pair. So here we have the length tuning, and you can also apply this length tuning for single and differential pair. And as you can see it here in the properties, so we have a lot of values in the properties for the length tuning. You can play around and specify the type and things like that. So the next one I like to talk about is configuring the vias, which is actually this is something very important here about vias. Majority of designers, they don't know about these things. Then they're only thinking about it is high speed is coming up to routing, and they don't consider about vias. So we are actually not impacting to the low frequency, and the significant impact is in high frequency. We have the different type of vias, and you can see it here like through hole, blind, buried, skip via, and then back drilling. In the picture, you can see the different vias as well in the presentation, plus the back drill. Let's go and see what is the via impact actually in the high speed. So if you have a look at this picture I have over there, which is the via here, and if the signal goes through to the via, so not all of those signals is going to the receiver. So some of those signal, some of the part of it is going to end of the via, and again it's coming back and go back to receiver. So as you can see here, we have a little bit delay because it's going back and it's going back to receiver. We get a little bit delay. And this is really important. The stop, we're calling it this stop. And the point is, you can see it in the picture, the via stop. And it's very important how long is it. If it is longer, that's going to take longer to get back and more delay. So radiating antenna, actually a stop is causing the radiation EMI, and also causing additional reflection, causing the crosstalk, and also it's very it has impact on the signal quality. So the next here, it is how can we minimize the impact of vias here. So the first thing is decrease the stop length, should be less than 10 mil, and the back drill constraints, which is, you can see it here on the picture. We have a design rule for that. You can actually go through to the design rules and have a look at this maximum stop length and tolerance, and a little bit changing the values over there. So what it does, this one, eliminating capacitive coupling, and also it is good for this antenna radiation. So the other impact of vias we can actually minimize, it's such as reducing the size of via, as you can see it here in the picture. So we have the constraints of via, which you can change it. The other things is removing unused pad shapes, which we're calling it non-functioning pads. And also you can increasing the clearance. You can use this power plane clearance design rule in Altium Designer to increase the clearance. The other impacts, which is actually minimizing the impact of vias, such as placing some stitching vias, is really good and is really helping to this provide paths for the signal return current, and also placement of some decoupling capacitors around the vias. That's going to be very helpful and for the carrying the signal return. Also the propagation via delay, which you can see it in the picture. We have this propagation delay in the properties. You can also using it in Altium Designer. So let's a little bit talking about X signal multi-chip very quickly, and that is something like for supporting the DDR4 and 3 memory structures and USB 3, which you can also customize it, a multi-component setup. You can do it from Altium, and we have the setting for that, as you can see in the picture, and you can go into all these setting for the X signal. And it's a very big topic, this one here. We cannot spend a lot of time on this today, but you can find a lot of documentation if you want to find out more about this topic in Altium Designer. So also here we have a pin package length, and this will specify the length from die to pin. So this is specific for FPGA, and for the design you might have for the FPGA, it is accessible from properties. As you can see in the picture, you can have access to that pin package length. So the last topic I have here for today, it is signal integrity analysis tool, which is very, very important and useful tool in Altium Designer and everywhere in a high-speed design. So we're going to identify with the signal integrity, this tool, we are going to identify nets that could have unacceptable levels of reflections. Also, predict the potential levels of signal refraction and crosstalk as waveforms. And also, it allows to actually help to select suitable termination components for component placements. And then also, it's going to allow you to set up the physical kind of the trace impedance from within the signal integrity simulator. So again, to remind you again what signal integrity does here, it is nets with potential reflection problems can be identified, and also any additional termination components can be added to the schematic before, which actually we go to the board layout. So even here in the picture, you can see we have a lot of rules for signal integrity in design rule. You can try them. The thing is about the signal integrity, it is really helping you to find out where is the issue of the crosstalk, EMI, and the component placement, because the length between pin to pin and all those you can identify in signal integrity before you go to board layouts design. So this is with the Altium Designer. You can also install it, the signal integrity, from your license in Altium Designer. So you only need to go to the license and go into the install signal integrity analysis. You can see it here and install it. Okay, guys, so we are going to have a little bit of the demonstration, which Stan is going to have a demonstration for what I spoke on the presentation, to making a little bit clear for you what is actually you can do with the high-speed design in your design and PCB design. So thanks for listening to me. And hi, Stan.
Yeah, hi there. I will take the presentation and I will share my screen so that you can see Altium Designer. And hopefully you can see my screen, everybody. So here in Altium Designer, I have currently a project and I'm using the cloud-based system that we have. So everybody in my team can actually access this from all around the world. So if Ida would help me, she could also help me here. This is the schematic we are going to or the project that we are going to play a little bit with today here. You see, this is a pretty straight ordinary buffer. And what you do have here is that I will use this buffer as a transmitter and this buffer as a receiver, and we'll try to see what we can simulate with these tools here. Now, sorry, you can also see that of course, in order to be able to do some simulations of it, I need some models. And if we have a look at the models that I have assigned for these buffers here, I have what we call an IBIS model. And the IBIS model is like a SPICE model that we use for the intents of signal integrity simulations. If we have a look at what's actually inside that model here, we will see that this specific model is actually specifying a 2.5 volt and a 3.3 volt three-state output here. It's also defining the inputs. So it's like a description on how the output buffer will react according to some voltage and currents that you will send to it. You will also see that I have the model type here. I am selecting a typical case, but I could also select a strong and weak case here. If we take the typical case, these data will be obtained for nominal supply voltage, nominal temperature, and nominal process parameters. Of course, if in a minimum or weak model, the data will be obtained with the lowest supply voltage, the highest temperature, and the weakest process parameter. And in maximum, these will of course be the highest supply voltage, low temperature, and strong process parameters. But for this simulation, I will only use the typical one, but you should of course, do all three simulations of them. I have currently selected down here the models, this three-state output, the 3.3 volt, but I could also, of course, also use the 2.5. It's that fits my power, of course. So this is how we set up the models for it, and these should of course be set up for all my integrated circuits in here. You can also see that I have placed what we call a signal integrity rule here. So I'm actually explaining the system that these are my power nets and they should not be included in the simulation. They will be used as power. Beyond that, I have what we call a parameter set. So these nets in this box here are all assigned to what we call a class, and that class is then called high speed. And you can see I have two nets in here. I have the nets over here and here. So these are all assigned as high speed nets. So already now I can do what we call a pre-signal integrity simulation. This means that I can actually simulate without having any PCB. So I can have a look at what it will be like. So let's actually do that. Let's go into the tools here and do the signal integrity. You can see that it's fully integrated into Altium. You don't have to start anything extra. You don't have to export anything. Now it just works inside the tool here. So let's have a look at it. You can see already it has done some simulation. So it says that this net here, that D0, this one up here, is actually passing. And in order to do so, we need to do some assumptions. So let's first see here the setup options here. So we are assuming that the trace impedance will be 50 ohm, and we have an average track length of 2000 mils or 5 centimeters, something like that. You can also see the supply nets here. I already specified this in the schematic, so therefore I don't have to do it in here. And I can also, if I want to set up a special stimulus that I want to use in this simulation, this is okay. And therefore, I have this simulation done already. And if we look at the tolerances for it, I have set the tolerances, say, okay, all the falling edge or rising edge overshoot is set as a percentage of the top value. So this will allow me to have like 10% overshoot and 10% undershoot, sorry. I can change this if this is needed. But I think this is a good setting. So having these settings, I see that all my signals that have actually a series termination here, they will pass my signal, even though it is a bit close to, but it will work. On the other hand, the signals that doesn't have this one here is actually failing. So let's do a small analysis of that. Let's add this net here into the analysis. and you can now see that I can simulate down here. You see the designator, the direction of it, and everything is visible here. If you click here, it will be highlighted in the schematic, so you see especially where it is. And now I can simulate with no termination as it is right now, and I can also enable a series resistors in here. Now I can let Altium suggest what kind of resistor it will, which one will fit most. But in my case, I think I will decide, so I will use a 39 ohm for it. And I can also perform what we call sweep, allow it to sweep from a certain range of resistors in here. But let's do the analysis. This will give me the waveforms. And as you see here, up here, these two signals here, you can see this one here and this one, these are my transmitting signals with no termination and with the series resistors of 39 ohm. Now, these signals is, of course, not so interesting because what happens at the receiver side is, of course, the interesting part. Here we see the exactly same signal coming at the receiver side. So we see a huge overshoot here, and we see a huge undershoot also here without any termination. If I switch to the termination with 39 ohm, you can see that there's no overshoot. So at least now I know that I should use a series resistors in here. Let's actually save this one. Let's save this one here. I will save this as, let's call it pre signal integrity test. Yes. And let's go back to the schematic. So I have figured out now I need resistors. I won't insert them here, but of course I should do that before first. Now let's add the PCB into this project here. Going to an existing one that I already did. And with this, it's now possible to do, of course, post simulation also. And this is, of course, the most accuracy because now I have the actual PCB. I know where the planes are. I'm not assuming 50 ohm anymore. So if we first look at the layer stack in here, see how the PCB is built. And in here, you can see that I am currently using a 4-layer board. I have 4 copper layers, one top layer, a ground plane, a power plane, and a bottom layer. This is like pretty normal. And then you have all the dielectricals, the prepreg in here, and the core in here. If I don't like this core here, you can see that this has a decay of 4.8 and a dF of 0.02. If I select another core from the material library, like this, a construction of 2-2113, I will get another decay factor if this is what I need instead here. Now, I will not use this one. I will simply go for this one here. Another thing that we need to address in this layer stack is, of course, the impedance. So let's switch to that. In here, you can see I am currently having a impedance called S50. And you can see I am allowing to route here on the top layer here, and I will use this layer here as a return path layer. It's also possible for me to route on the bottom layer, and in that case, the return path will be this layer up here. If we look at the top here, you can see the properties for it. I have set that this should be a single trace with a target impedance of 50 and a tolerance of 10%. Now, I'm also saying that since this is a outer layer, the edge factor, the process factor, or what you will call it, is 1.4. That this means that the copper will be wider here than it is on the top of the trace here. Having all these data here will then give me a target impedance of 50.02 ohm. This is my deviation. And my width of the track should be then 4.6 mils in order to achieve this 50 ohm impedance here. I could also say that it's not a single one. I could say that it's a single coplanar track. This means that my track is running on the same layer as my reference layer is also. So I am referencing to a polygon that's next to the signal. Now, of course, this also applies to differential or differential coplanar signals, so we can do both of them also. So these are my settings for the PCB. So if we go back to the PCB, in here I have already placed my component and I have done some routing of it. And you can see here, if we look at the trace length here, the width here is 4.65. So this is exactly a match with the impedance rules that I have here. There's also some design rules that we need to have a look at in here. The routing width, in my case, I have two here. And this is the one for the 50 ohm impedance here. So if we have a look at it here, I have assigned that this rule should apply for all net classes belonging to the high speed. So every net that has this been assigned this class will have to obey this rule here, and I'm using the impedance rules here at 50 ohm. Now this will give me those two tracks to route on, and the preferred width should be something like this instead. So having said all of this, I am now ready to do a simulation, a signal integrity simulation of my actual board here. So let's actually do that. Let's run the signal integrity tool again. Now with the board, bring it in here. And you can see that every net is passing. This is of course good. If we look at this net here, this was the one that we looked at. The falling edge and the rising edge are like very small. Nothing goes beyond 50 milliohms, 50 millivolts, sorry. But if you look it down here, you see that D4 here, that has a massive overshoot, but it's still passed. So I of course need to adjust my tolerances. Just do that. You can see here, I am actually allowing up to 300 volt. So everything will basically pass in here. So let's undo that and see, okay. And now they will fail, of course. And now I can do exactly the same as we did before. I can put this into the analysis and say, okay, what kind of termination should I have in order to achieve a good signal integrity? Let's wait with that and instead do something a little bit stupid. So we will change the impedance here in the PCB, and we'll see what effect that has on the signal integrity. Let's go to the stack up here and change this to a 75 ohm and go back to the PCB. I'll save it and go back to the PCB. And now my tracks needs to be rerouted. So I'll just go to single layer mode like this, and I will select the tracks like this. And I will ask Altium to do it. Actually, just retrace the selected trace now. You can see that they are like very small now. And this is because they have to obey into the 75 ohm now. So these will match 75 ohm now. Let's redo the signal integrity in here. And as you can see, they are still passing the nets here, but you can see I have more now. I'm very close to my defined rules now. It should be 330. So I'm very close to the limit here. And of course, the signals here is still failing, of course. Okay, so that is what you can do with the signal integrity tool. It will give you a good view about your signal integrity in all your signal. As you can see, it's very fast to calculate it also. Let's, on the other hand, have a look at the bottom layer here. I have some tracks here. You can see that I have squeezed them down, so they are like very close. D4, 5, 6 is very close to each other. So let's actually try and do an analysis of the crosstalk between them. Again, I will start the tool, signal integrity. And in here, I will do the analysis of the data signals here that I have. So I will add, let me just finally, I will add this net here to the analysis. And in here, I will say that D4 here should be set as aggressor. This means that he will carry the signal and the other ones will be the one that are receiving the signal. You have the information about where it comes from and where it goes to here. In my case, I will not use serial resistors here, only the no termination solution will be calculated in here. But I could, of course, try to simulate a serial resistor here. Let's do the crosstalk waveforms. Takes a little bit longer time, but here we are. So first of all, we see the signals are being transmitted here. And down here, you see that this is the receiver, the D5 on the receiver end, looking at the receiver end, and D5 looking at the transmitter end here. And you can see that I have like a overshoot, almost 1 volt will be actually coming from here and be reflected into D5 here. If we go down a little bit on here, you will see that I have, see this picture here, the D6 here at the receiver end here. You see that I still get reflection for it, but it is of course a little bit smaller than the other one, right? It's only 450, right? This is almost 1 volt here. If we go even further away from the signal here, looking at D6, D7 here at the receiver end, you can see that I'm still getting some reflection, but we are down to like 400 millivolts. So this one here, let's actually save this one. Let's save this one as Crosstalk. So this will tell me that it might be a good idea to separate the tracks a little bit more in order to not having these crosstalk issues now. So once I'm done with all my analysis here, the signal integrity, the crosstalk analysis, I can simply save all my project files here. And I will then save it to my server. So it goes to the cloud server solution that we have. Just type a note. So I will commit and push this into my server. And now everybody in my team has all my results, all my schematic sheet, my PCB, all my results that I actually did in here. So that's it for me. I hope it was useful for you. And I will stop my sharing and go back to Dion.
Thank you very much, Sten and Ida. They were excellent presentations. It's certainly the case where I think the amount of layout, the physical layout, made such a difference to that signal integrity. And I think it's a good example of where we're adding the art into technology and making the STEM into STEAM, because it really makes such a difference. Okay, well, we've probably got some time for some questions now. We've got quite a few questions come through on our chat panel, so thank you very much, everybody, for sending those through. We obviously can't answer them all, but I've got a selection here. So one of the first questions relates to the simulation tool and obviously being able to make changes at the PCB level to improve the signal integrity, but also with regards to the schematic layout as well. Have you any advice onto how changes at the schematic level and the board level can make the difference to the signal integrity? So should it be done at the schematic level, at the PCB level, or perhaps both? Over to you, Sten.
Yeah, if we start with the schematic tool, I would of course do the pre-simulation stuff. That will tell me if any kinds of termination is needed. Like here, we saw here, I need a serial termination. It doesn't really matter if it's like a 39 ohm or it's like 50 ohm. It doesn't really matter. The most important stuff is that I'm aware that I need this termination, and then I can place it on my PCB. It's very fatal to know this stuff after you actually done the PCB, right? And then you need another resistor. It's like hopeless to get in there, right? So I will do it firstly, do the pre-simulation into the schematic tool, and that will tell me if it's needed or not. And then I can do the layout, and the post-simulation is like more confirming me that I have the right impedance and so on and so forth. And I can adjust the values of the series termination there.
Excellent. Thank you, Sten. I think that's a good example of where good foundations yield good results. Don't just leave it to the PCB. It's kind of a holistic design right from the start. Another question with regarding the simulation tools. Obviously, this PCB design package contains excellent simulation tools. In your experience with regards to practical applications, how close are you finding that the software simulation matches reality? And presumably as the next stage of testing, you would do some hardware verification of that. Would you recommend to the audience any kind of simple hardware verification tools that they could use as part of that integrity testing?
Yeah, the simulation is pretty good, actually. It is not as... There are tools out there that are way better, but they cost like a fortune, right? And of course, if you have the money to spend on that, I think you should go with those tools. But it doesn't really matter because this tool here will actually tell you if a termination resistor is needed or not. And if it is needed, all you have to do when you actually build the PCB, you do have the resistor there. It's just a matter of adjusting the size of it. So should it be a 39 ohm? Should it be a 50 ohm? You can do that validation with, when you have an oscilloscope and you're doing some testing on it, physical test it afterwards. Then you will do, you might have to adjust your bill of materials after that. But I think that's very common actually.
Great, thank you. That's well answered. And a quick question, maybe not a leading question, but with regards to auto routers, obviously fine tuning would be required with any auto router, but how with relation to the signal integrity, how do you find that the auto router performs in those areas?
I think that it's actually performing quite well because the auto router in our system is dedicated to high speed, so it will not perform. It will not place any vias in there. For instance, it's a point-to-point router. So if you need, for instance, coming out of a BGA, you need to do the escape routing first for it, and then we can let the auto router do the rest of it. So from that point of view, the auto router is very nice. It doesn't place any. You don't basically want vias when you're doing high-speed designs. It will also, of course, take into account these track width, of course, and the track width is again related to the impedance in the PCB. Like you saw, I could set up a width rule here. So in that case, the auto router will, of course, take into the account that I have all these rules, and it will, of course, follow them.
Excellent, thank you. And a question close to my heart with regards to ground planes and extra layers. Obviously it's a whole topic in itself, but just some quick advice on maybe adding extra ground plane layers to improve the signal integrity. Obviously nowadays the cost of boards is becoming less and less, so there's more opportunities for us to go to 6-layer and plus boards. Just a quick advice on adding extra layers.
Well, as you saw in my demonstration, I have the luxury of a full plane. So this means that this was a total copper plane, and it's, of course, if you have the option, you should do it because it's very good when you have that way. You will have a very good return path in there, actually. If you don't have that, you will need to have like a polygon or something else following the track around, making sure that the track and the return path copper is actually following each other. And in Altium, you can set up a design rules like you saw Ida's presentation. It's possible to do that. So making sure that then the tool will kind of like validate if your signal is leaving this return path or copper in another layer. So that is also possible in the tool. I didn't have the time to present this in here actually.
Thank you, Sten. That might be a good segue into the next question, maybe more related then to Ida's side, would be regards to the dielectric used for the PCB. So obviously whether we're using FR4 or perhaps it's a ceramic base or perhaps even some form of insulated aluminium substrate. How does that play a part in the integrity? Obviously different frequencies, and how can that be accommodated for in the design of the PCB for the different dielectrics?
I think I'm not really actually sure very much about this, how much it can be, because it depends on the materials you use. In the data sheet, you can find the materials, and I mean, like, the important factors for high-speed design, depends on what materials for dielectric you use, and this depends on the data sheet you have. But I think can Sten answer this question a little bit more specific?
Well, I think actually you kind of did actually because if you're changing from FR4, that they will have DK and DF factors according to the material. And if you go for a ceramic, the DK and DF factors will change dramatically, and that will of course influence the impedance in the PCB. So yes, it will have a huge influence, but of course we will recognize that it's another decay and DA factor, and we will recalculate the impedance based on that, of course.
Yep, that is information actually. It is in the data sheet as well. You can find out as many. It depends on that materials you use actually. That's why all the information you have regarding DF, DK. So you could find them in the data sheet and then put and place it in the materials library in the Altium Designer.
Yeah, and just a sidekick to that is that if you want to design something, it's always a good practice to be in good communication with your PCB manufacturer, because they will know these factors, right? So if you tell him, I'm going to use a structure called 2-2118, he will know exactly what it is, and he can give you his information about the DK and DF factors. So always be in good communication with your manufacturer.
Great, thank you for that. That's a good answer. And a question regarding different shapes of pads for devices, probably especially through-hole pads, and the different impedances that some of those component pads may have. Does the change in the impedance based on the size of the pad, is that factored into some of the analysis that the tools provide?
Well, the tool is using the Siberian. It's a 3D simulation tool. So I would reckon that the pads and VS is of course also calculated into these impedances.
Excellent, thank you. And just with regards to some very high speed PCB design, so if we're going to say more RF applications, I know that RF PCB design is kind of a bit of a black art of the radio magic that might be in there. Some of the tools that you've shown us today, what is the kind of maximum frequency that those tools are designed to go to? Do they go into the RF spectrum, or are they limited to any limit?
Well, basically no, because what we can do with the tool is that we can calculate the impedance for you, and thereby actually having the width of the tracks that you should route. And if we go into RF signals, in our case, it's more based upon the rise time and the fall time, not exactly the repetition of the signal. And of course, if you have let's switch not to RF, but take something very high speed like 10 gigabit Ethernet or something like that, 50 gigabit Ethernet. They have like very high or very fast rise in edges, and I think it's a bit the same, right? It's really a matter of the impedance in the track that you are routing on. And of course, the return path is very important.
Thank you. Probably one final question, which is probably more a mechanical question perhaps than an electrical question. But I guess once we get into high frequency, those two become much more interdependent. With regards to the PCB being mounted into an enclosure, and that enclosure has probably been designed with some 3D tool, is it possible to include some of the mechanical aspects of the enclosure, especially with regards to the shielding, in some of the analysis for the signal integrity based on the closeness and the capacitive coupling to the enclosure, for example?
Currently, no. We can, of course, check the mechanical aspects of it. So we can check if you're placing a connector, does that collide with the enclosure? That is possible to check in Altium. You can simply import the 3D step model into Altium and see if it fits there. But the simulation will not take into account that you have something like a shield or something. It will not do that.
Okay, well that's fine. Well, thank you very much for answering all of those questions. And I guess really we're probably limited by time, just very mindful of the time. I would ask that everybody has an opportunity at the end of the presentation when the survey, a survey form will pop up in the web browser asking you for your comments on the presentation. I would certainly encourage you to fill in that. Also in there is one of the boxes which says, have you any further comments? If you have any questions that haven't been answered this evening, if you could type that question into there and perhaps your email address, just to confirm that the speakers will be able to contact you directly, we can answer some of those questions that you might have. So I'm afraid that's the end of tonight's presentation on high-speed PCB design, and I hope that you found it really interesting, and I certainly have. So really, I'd just like to take this opportunity to thank you all for attending, and also to thank the various people that have brought this together for you from the institutions, not least of all Ida and Sten for their wonderful presentation. Moving forward, when the social distancing restrictions become a little less stringent, we hope to continue some more of these webinars and also the physical events at Engineers Australia's new location in Market Street in the centre of Sydney. So please keep an eye on the website for any upcoming events and their locations, and to also check out the various social media channels, etc. And you will also be sent a link after the event to access some of these presentations which are recorded for your future enjoyment. So until then, I thank you all for your attendance, and again thank you to Ida and Sten from Altium for their great presentation. We look forward to seeing you all again, and until then, please stay safe and have a pleasant evening. Thank you.